All right, we're gonna get started. Thanks for joining us today. So today we're talking about 3D performance modeling made easy. This is the introduction of PlantPredict v12, which includes now the 3D shade modeling, which is a first for PlantPredict. So in today's agenda, we're going to give a quick introduction about Terabase and PlantPredict, some quick presenter intros. We're going to go into a description of what's new in version 12. We'll have a live demo of how to use PlantPredict 3D features within the application. Then a technical spotlight on some of the details that went in to our 3D features. Then one more live demo on how to use those 3D results, some closing notes, and a Q&A. So if you have any questions during the course of the webinar, feel free to drop those in and we'll be taking a look at those right at the end. So first, a little bit about Terabase Energy. If you're not familiar, Terabase is building a digital and physical solution ecosystem to help accelerate the deployment of solar, and that's what you see on screen here. First, on the left, we have our software and services for the development and pre-construction phases of the project. And of course, central to this is PlantPredict, our solar energy modeling engine. We've been expanding PlantPredict into a full suite of professional design tools, including layout automation, material estimation, economic modeling, and grading analysis. We also have construction products and services, including construction management and monitoring software. For the physical world, we've built an install automation solution called TerraFab, where we bring a mobile factory to your project site, complete with an assembly line and rovers to automate the module to torque tube to pile assembly. We've installed more than 40 megawatts to date, and we'll be scaling up to hundreds of megawatts in 2025. Finally, we have our plant controls team that provides a full set of SCADA and power plant control services, including hybrid control systems. Of course, PlantPredict, there's the core product. And the new introduction today, one of the biggest updates is the introduction of 3D shade modeling. It's available now and included at no cost for all paying customers. We also have our other pro and enterprise tools. And we have some more, our PlantPredict team also builds more advanced tools if you ever want to contact us for CAD-ready earthwork analysis. All right, and then I'd like to introduce today's presenters. We have Jason Spokes, our Senior Product Director of PlantPredict. He'll be giving the demos of the software today. And then we're also being joined by Kurt Reed, Product Owner for PlantPredict, who will be doing a technical deep dive into the topic of 3D shading and explaining some of the computing we're doing behind the scenes to run the 3D analysis. But now let's kick it off with Jason.
All right, thanks for fall. I'll go ahead and take control. Let me share my screen. Okay, so hopefully everybody can see my screen. I'll go ahead and turn my camera off. All right. Okay.
Jason, we can't see your screen yet.
Oh, you can't see my screen yet?
No.
Sorry about that. Screen. Okay.
There we go.
Okay.
Thank you.
Okay. Good stuff. Okay, so let's get rolling. So what's new in version 12? So first of all, version 12 is currently in a beta release stage, and this means that version 11 is still the latest stable release and will be the default version for new predictions created. You can access version 12, which includes all of the features we'll be talking about today, by switching the version within the prediction page, and I've got a screenshot over to the right here, and I'll show you how to do that during the demo as well. One of the advantages of PlantPredict is the ability to easily switch between stable release versions and the fact that past versions are frozen. The primary new feature that is in version 12, of course, is the new 3D shading scene and model, which Kurt and I are going to be discussing in a fair amount of detail today. We also have an exciting new integration with ATI, Array Technologies, which I'll be talking about in the next slide. And some other notable improvements from version 11, which affect the energy performance model, is the handling of tracker actuator loads. So these can no longer be applied to fixed tilt systems, which I think was mistakenly done in the past, more than probably should have been. We've implemented some improved handling of auxiliary losses within certain of the output performance parameters. We've corrected some of the irradiance loss calculations when trackers are manually fixed at 0 degrees. So why would you want to manually fix your trackers at 0 degrees in the prediction? Well, if you're running a capacity test, for example, and you're matching what the system has said in the field, you might want to force that. So we've run into some issues in the past, which we've corrected in this latest version. We're now correctly imposing backtracking rotation limitations for irradiance optimization backtracking options. And then it's not really doesn't really affect the energy model, but we have updated our CSV nodal data downloads encoding to UTF-8. So this is a much more user-friendly format when working with these files programmatically. All right. Next slide. There we go. Okay. So the Array Technologies integration. So for trackers, if you've selected backtracking, we have a new ATI irradiance optimization option. And I've shown a screenshot of what that looks like, what that option box looks like from the DC field within the prediction. If selected, PlantPredict will send certain data to ATI, specifically your weather data or certain parameters from your weather data and a few design parameters like ground coverage ratio. And ATI is going to return their proprietary smart track rotation angles for each time step. So those smart track rotation angles are then going to be used within the prediction. So in order to run this, you have to set up your prediction with a 15-minute interval weather data set. And your prediction, and you must have an ATI API key, which you can request from the email below. And what's really exciting about this is really, for the first time, we're really, combining the same sort of algorithms used from the hardware supplier that are going to be embedded in their field control hardware. So, this is kind of a first step into that world, which is pretty exciting. All right. Next slide. So before we get into the demo, I wanted to say a few words about PVC file format and its compatibility with other applications. With version 12, in order to bring 3D racking geometry into the shading scene, we need to supply this information via a PVC file upload. So what is a PVC file? So PVC files follow the Collada file standard for 3D objects and scenes. So you may be familiar with the DAE file extension. So these are Collada files. But they differ from the standard Collada file format in that they include special information unique to PV systems, such as whether a particular object is a fixed tilt or tracker rack, as well as where the rotation axis is for that particular tracker, if it's a tracker system. PVC files can include non-PV shading objects, such as trees, windmills, buildings, etc. And they don't include any electrical or mechanical relationships. So for example, you're not going to be able to get, for example, this rack is connected to that inverter. That type of information is not contained within the PVC file. But there is an ongoing industry working group to build more information such as electrical hierarchies, mechanical hierarchies into PVC file format, and Terabase is one of the participants. Finally, PVC files are not georeferenced. So they are not tethered to a particular location on the Earth. In order to get that information, we have to couple that with other information supplied by the prediction. So the PVC file is really defining the geometry, and then other aspects of the prediction, within PlantPredict, we define the project location separately as part of the project, so that information is supplied separately. And in the below graphic, trying to illustrate the fact that there are a couple of different ways to generate PVC files. In the Terabase world, there's 3 different ways to generate PVC files today. And for today's demo, I'm going to be highlighting how to do this from the PlantPredict map builder interface. But it's also possible to get even more detailed, especially from a grading and racking mechanical perspective within Design Pro and Terrain Pro. So both of these applications now allow you to export PVC files of your 3D design. Additionally, there are at least several other third-party PV design applications which can export PVC files. So you might be familiar with VertoCAD, PVCase, Rated Power. These are some examples of other applications that can generate PVC files that can be imported into PlantPredict now. And similarly, it's also possible to import PVC files into PVSys. So this is a standard way to define a 3D shading scene in PVSys is via PVC file. So hopefully you can see that the PVC format is starting to become somewhat of an industry standard and used between different applications. Okay. So with that, I think we're ready for our first poll question. And so poll question number 1, what tool are you currently using to evaluate 3D shading? And looks like the poll is live. So we have PVSys, PVCase Yield, Solar Farmer. Maybe you have some internal tools or other. And maybe if you're one of the folks in the other category, feel free to drop that into the chat. Curious what people are generally using. Okay, so the results are coming in clear. It's pretty clear that PVSys at 58%. Most people are using PVSys. PVCase Yield at 4%, Solar Farmer 11%. Internal tools actually 18%, which suggests that quite a few people are using internal tools to model 3D. And then other at 9%. So I will close the poll. Back to the presentation. And so that sets us up for our live demo. So let's step into that. And I'm pulling in my browser. Hopefully everybody can see that. All right. So at this point, you can see that I've already predefined a site boundaries and constraints for a fictitious project in Virginia, which is located next to an existing solar plant. And right now I'm within PlantPredict's map builder. And really what I'm going to be trying to show is I'm going to go through the process of setting this up from a 2D perspective. And then I'm going to clone it and create a 3D variant of it and run through the process of actually bringing that into the shade model. And then ultimately, at sort of the end of this, we'll go through the results and see the differences. Okay, so I've set my project up with an SMA Sunny Central 4400, First Solar 7540A. I'm targeting a 40 megawatt DC system, 1.2 DC AC ratio, and I've currently set this at 40% GCR. Of course, I can look at other parameters, but let's go ahead and update the DC capacity and see where we fall. Okay, so that has populated our array layout If we look at the system specs, we're at 36.4 megawatts DC, 30.8 megawatts AC. And just sort of going through, maybe I'll get rid of this particular rack because it's out in no man's land. But other than that, I'll go ahead and keep that, at least for the purposes of today's demo. And I am going to save progress, and I will X out of Map Builder. Okay, so that brings us back to the prediction page, which you're all familiar with. And in the prediction page, we were just in the PV blocks and arrays sort of design area. So this is where we can enter the map builder space and design the system on a map. But this is also where we can enter weather data, which I've already done, and a number of other sort of model information. I want to draw attention that we're currently in PlantPredict version 11. So if I want to change to version 12, which is where the 3D shading scene is, this is how I can do that, and I'll confirm that choice. So I'm stepping into version 12 beta. And you'll notice that now there's a new option within the power plant specifications, and that's the 3D shade scene. So I'm not going to do anything with this right now. I'm going to leave this sort of blank. And I'm going to go ahead and run the prediction. And this is going to be our sort of 2D version of that prediction. And after this runs, I'm going to clone this particular prediction. And I will make that clone as the 3D. And so I'll go through the steps of how to do that. All right, so the prediction has run. We could step into the energy results. I'm going to hold off on doing that for now because we'll do that at the end when we're comparing the 2D and the 3D. But what I'm going to do next is I'm going to clone this. And it's going to take a second to copy the information to a new prediction. But this clone is now going to become our 3D prediction. All right, so we now have our clone. I'm going to rename this to 3D. Okay. And so let's step back into the map builder for a second. And you can see that this is the same design that we were looking at before. And if I wanted to generate the PVC file for this, it's as simple as going to download data, PVC file, and hitting the export button. And when I do that, what's happening is PlantPredict is pulling in the publicly available topo data from Esri, and it's basically draping the racking over that publicly available topo data. Now, alternatively, I can upload my own topo data, so I can upload my own digital elevation model data here. For today's demo, we're just going to go with the publicly available data. I can also look at a 3D view before I download the PVC file. I can also look at a 3D view of the power plant. And can I expand this? Okay. And when I do that, you can see that there's clearly some rolling hills, some terrain here. I can adjust some slope constraints both in the north and south direction. And what that does is it pulls in some constraint information, or it pulls in some slope information. And what I can do is, if I wanted to, I can convert these to constraint areas to avoid. I'm not gonna do that for today's demo, so let's turn off those layers. And let's just simply go to the download PVC option. So I'll export this. And it is PlantPredict1 is the file name. So let's X out of this and go back to the prediction page. Now, before I go into the 3D scene, there's one other thing I need to show, and that is in the simulation settings, there is a new field in the shading models called 3D shading, and there's two options. There's DC field and site shade scene. The DC field refers us to that same DC field way of defining shading. So there's no changes to this option, and this is basically how we ran the previous 2D version of PlantPredict. So if you're looking for some more information on what options are available in the DC field, again, this is not a change, and this is really the same as version 11. What is new is the site shade scene. So I'm going to select this because what this is going to do is it's going to point the prediction to the site shade scene for the beam shading. So I'm going to save and close. And you'll notice that when I did that, there's now a new line item that's required prior to running the prediction. So the 3D shade calculations. So this is telling me that I have not run my 3D shade calculations yet. And so let's do that. So I'm going to step into the 3D shade scene. And the first thing I'm going to do is upload my PVC file. All right. And you'll notice that this is the same layout as what we had before, and it is a 3D layout. If we inspect it, there is definitely some contours here. And again, this topo data was pulled from a publicly available source through Esri. And if we inspect some of the options, there is a binning type option. So we haven't run any shade models yet. We're about to. There's some binning type options, which Kurt is going to talk through what this actually means as part of his presentation. There is the ability to rotate the scene by 180 degrees, and this can be helpful. You know, we don't control all of the third-party applications that generate PVC files, and sometimes if you're working in the Southern Hemisphere project, for example, it may be necessary to rotate this around basically around the 180 degrees around the origin. PVSys has a similar option to do this, so this is just a helpful option without having to reformat your PVC file. And then we can see some information about the prediction or about the, how the shading engine is going to run. So this is a horizontal tracker. True tracking is the algorithm that is going to be employed. The radiance optimization is disabled, and the GCR is 40%. And so from a direct beam shading perspective, the scene is going to be using the geometry here. The GCR is really informational provided from the DC field information. One last thing before we kick off the simulation, we can go into the shading sim part, and we can go on a time-step by time-step basis and sort of visualize the shading for a given hour. So let's zoom in a little bit, and we can start to see some shade on some of these trackers. And we can see that the tracker rotation is going from east to west, which is what we would expect. Okay, so let's go back. Let's go ahead and queue up these 3D calculations. This is going to take about 2 minutes to run. And just for a context perspective, I believe there's about 2,000 shading objects or 2,000 racks in this particular scene. Currently with the 3D, the beta version of version 12, we have a 30,000 object limit. So just to give you some perspective as to system sizes that can be put into this. And with that, let's step back into while this is running, let's step back into the presentation. And I think this sets us up for poll question number 2. So what is your biggest pain point in performing 3D shading analysis? Is it obtaining accurate topographic data? Is it creating an accurate racking layout in 3D? Is it importing 3D data into your performance model of choice? Is it system size limitations in 3D modeling tools, or is it processing speed, processing time? So the results are coming in. Thanks. Give that a second. Okay, and so it looks like things are pretty evenly distributed with maybe a kind of the leader, about 26%, creating an accurate racking layout in 3D. Also, similarly, 24% obtaining accurate topographic data, and then 15% importing 3D data into the performance model, 19% system size limitations in those tools, and then 17% is processing speed. So I'll close the poll. And with that, I think I will turn it over to Kurt. Kurt, you want to take it away?
Sure. Yeah, those poll results just show that everything's hard in 3D. Um, okay, so this part of the presentation is sort of the theory and the computer science behind what PlantPredict is doing. Um, so starting off, there's sort of two different distinct families of 3D shade calculation algorithms. And right now I'm talking about beam shading. The first family that people are probably most familiar with is the geometric family. And that basically gives you a 3D representation of a site um, in with vertexes. So you have an XYZ point that's representative of an edge of your module or bay, and four of those points create some polygon that represents your tracker geometry. This sort of family of 3D shade calculation algorithms is sort of accurate to the floating point accuracy of your computer, um, meaning that it's basically entirely precise, and all of the uncertainty comes from how good is your topography data, how good is your 3D twin of your site, physical twin of your site relative to what's actually installed. The next family, like pixel counting family, adds on another layer of uncertainty, which is basically how many pixels do you have, are you using to compute, or how many rays are you shooting? And pixel counting, people who are familiar with like the movie CGI industry or um, the video game industry, uh, they don't necessarily need to get mathematically precise shading, and so it's really commonly used um, in those two industries. And that's not to say that pixel counting or geometric families are right or wrong. If you have enough pixels or you shoot enough rays, you can get a totally photorealistic um, version of the 3D shade calculation. It just adds another layer of something to think about. Um, let's go to the next slide. Okay. Um, so these are some common approaches to 3D shade modeling that are used in the industry today. Polygon clipping is what's used by PVSys and PlantPredict for at least the beta version. We're also looking at some of these pixel counting algorithms and doing some sort of fundamental research to see if we can get the shading calculation to be much faster with some acceptable level of accuracy. The pixel counting approach is attractive from a speed perspective because you can parallelize on the GPU instead of the CPU. So you could theoretically have 2,000, 4,000, 8,000 cores working on the problem instead of 6, 8, 32, let's say. That research isn't complete, and I'm not going to talk about it too much, but look forward to that in a future version. Um, Many of you probably don't know, but PlantPredict also has another pixel counting 3D shade algorithm already implemented, but it's limited to a single DC field, and that uses the 3D shadow volumes. Um, some of the pixel counting methods are also attractive because they inherently give you the diffuse and the reflected components, um, such as ray tracing. But it comes with a computational cost, so we have to weigh uh, the increase in fidelity versus the compute speed. Let's go to the next slide. So talking about uh, polygon clipping, which is the computationally simplest approach, it's already quite hard. 2D shade is O of 1. This is a time complexity chart, kind of like computer science 101, is you want to know how your algorithm scales with the number of inputs. So as the number of inputs increases on the x-axis, the number of calculations that you have to do goes up by a certain amount. Um, Transposition is O of n, meaning for every new directional sort of like normal vector of your plane, you have to do another calculation. 3D shade modeling is O of n squared if you do it brute force, which means with each input, you have to compare it against every other input. And you could see how when the number of calculations or the number of polygons gets to like 30,000, how O of n squared might be a really difficult problem to solve. There's some algorithmic tricks that you can do to get to O of n log n, but that's sort of like the theoretical limit of how fast you can do a 3D shade model. So 3D shade will never ever be as fast as 2D shade, and it's a limit of computation. Next slide. Okay, so in programming, there's sort of like three regimes of um, program speed that you can get into depending on which language you're using. AOT stands for ahead of time, and so basically you compile your program and then the program that's actually running on your servers in the cloud has already been compiled. There's no additional compilation that has to be done. So you compile it once and then it runs a bunch of times. JIT compiled, JIT stands for just in time. Basically what happens is your computer will run some of the, let's say the for loop that you've written, and it'll look at this for loop and say, okay, I can compile it in this way to run faster. And it'll do that in the background and then you'll run it. So there's some amount of time penalty you pay when you use a JIT compiled program compared to an AOT compiled program. And then most people here are probably familiar with Python, which is an interpretive language, and interpreted language basically compile line by line. And that's obviously the worst in terms of speed, but it's great for flexibility in writing scripts. Currently, we're in this JIT compiled regime with the code that we've written in this beta version. By the time this gets fully released, we'll be in the AOT compiled regime. So I think we'll get like a 4 to 10x increase in run speed. Next. So architecturally, something I think that's kind of a little bit interesting is that there's a set of workers in the cloud that runs predictions, and there's a set of workers in the cloud totally separate from the prediction engine that runs these shade engine calculations. So you'll never get sort of like crosstalk or having a bunch of predictions delay your 3D shade workers or vice versa. And theoretically, you could talk to these workers via the website UI like Jason just did, or through the API or the SDK. Practically, as of right now, um, we haven't written the documentation to tell you how you would do that through the API, and we haven't updated the SDK to allow you to do that. So that's work that's currently in progress. One of our developers is writing that documentation right now as we speak. Um, the A lot of people get confused about what the API and the SDK is and how they're different from each other. The API is how PlantPredict does all of its work, how it gets information from the web UI or from someone connecting to PlantPredict programmatically. The SDK is just a Python wrapper that's on top of the API that basically translates from Python to this REST API speak. Next slide. So what have we done? We've looked at this is a paper that got presented at the PVSE and PMC conferences. If you're interested in the paper, just shoot me a message. But we were interested in sort of the interplay between different terrain scenarios and the different types of bidding strategies that you could use to speed up your shade calculation. And so we took a sort of like an egregious site, sort of like impossible to build terrain, used PlantPredict's Terrain Pro software to grade it to match the mechanical specifications of the Nevados tracker and then the Next Tracker XTR tracker. And then we graded it completely flat to do a standard tracker. Go to the next slide. We're going to do a really quick overview. But when you bin your zenith and your azimuth by 1 degree, you basically get statistically indistinguishable results from just running every single time step with no binning. And every single time step meaning every single possible sun angle in your weather file. And that's across all of the terrain complexities that we modeled. The next slide. So the bin width that people are most familiar with is the 10 degrees, 20 degrees bin width from PVSys. It's called the fast mode. And what we saw across all these terrain scenarios is that your general directionally, your mean bias errors is still pretty good. But you do get some degradation in the like time step by time step and root mean square error fields. I think for most scenarios, the 10 degree, 20 degree zenith is a totally acceptable level of interpolation. Next step. So now what everyone's interested in, how is PlantPredict different from PVSys? The first point is that the PVSys fast mode does a full grid, and it's a concrete grid, as in at 70 degrees of zenith, at negative 40 degrees of azimuth, they are taking that exact point, and then calculating the 3D shade results. Next slide. And that's in contrast to PlantPredict's way of doing it, which creates a fuzzy grid. And basically, we do a search throughout your weather file to find at 70 degrees of zenith, 140 degrees of azimuth, what is the closest sun angle that we can find in your weather file, and then use that as a grid point. And the reason we do that is because, unlike PVSys, you can enter your own custom tracker angles in PlantPredict. And if we used a set grid, we wouldn't be able to use the the rotation angles that you, the user, have specified. Next slide. And then this is kind of like a roadmap slide of where PVSys is at and where we're going to get to once we release the v12 as stable. So currently we both have 3D rotor-row shading. The polygon limit for PVSys depends on what laptop you're using. So if your laptop has more memory, you'll be able to run larger sites. We have fixed servers in the cloud, and we specify how much memory these servers have. And so right now our limit is 30,000, which is around 1.5 gigawatts of standard trackers. And we're working actively to increase this number so that you can do more terrain following trackers, which have more bays in them. We currently don't have terrain shading, but we're working on it. Same with object shading. We're working on the user experience for partitions, electrical partitions. And if you're familiar with the concept of active areas, physically when you have a module, there's from the middle of the module, you have a set of cells, and then there's like a small gap and there's an encapsulant in this small gap, and then there's a frame. And you don't necessarily want to model the shade calculation on the encapsulant and the frame. So we're working on some UI elements to let you specify how large that active area is, and then include that in the 3D model that we sent to our shade engine. Sort of forward-looking, we would like to work on in the next version, terrain-aware backtracking and the 3D transposition that comes with it, where if each tracker is at a different angle, you'd want to do a new transposition model for each one of those bays. And we're also looking into how would we supplement our beam shading with diffuse shading. Okay, next.
All right, so that brings us to our third and final poll question. Thanks, Kurt. That was great. What is the largest source of yield uncertainty related to 3D shading? So the poll should be open. Is it topography or grading data, near object shading from trees, buildings, windmills, etc.? Electrical shading losses, so being various types of module and string mismatches due to shading. Proprietary terrain-aware backtracking algorithms, or the lack thereof, or other. So results are coming in. Thank you. So topography and grading data being the highest at 37% of respondents, and then the next three being pretty even. Near object shading, 18%, electrical shading losses, 22%, and then backtracking algorithms, 20%. So thank you for that. That's great. Close the poll and move on. Okay, so that brings us to the final portion of our demo. And just a time check, we've got about 15 minutes left. Let me pull in, go back to PlantPredict. And so what I'm showing here is the completion of the shading simulation run that we had queued up prior to Kurt coming and speaking. And what you're seeing here is a heat map that ranges in a gradient scale from 6.3% at the lowest in green to 27.59% at the highest in red. And this is a relative scale, so the scale itself changes depending on, for each, scene, each simulation. We also have a absolute scale which bends shade fractions into these sort of static bins. And so a good way to think of these two different options for viewing the data, the absolute heat map is good when comparing maybe two different scenes or two different designs, two different projects, and then the relative is good. I think it's most helpful just trying to inspect what's going on a particular site. But you can see that there's some, definitely some higher red areas in terms of higher shading losses in the valleys, which kind of makes intuitive sense. So this kind of worst area here, we can see that this is kind of in a depressed area, and that kind of makes sense. We also see that the edge trackers generally have lower overall shading. And then I think another sort of interesting takeaway here is that we're getting some higher shading losses, higher beam shading losses on the north-facing side of the system, which is intuitively makes sense compared to the sort of south-facing side of the system. But I want to take a minute to really explain what these percentages mean. So these are the beam shade fractions. And remember that at this point, we're only analyzing the shade fraction for each time step on a particular rack or bay. And this is different from an irradiance loss or an energy loss. So this is not, these numbers may look quite high if you're used to looking at shading losses in terms of energy losses. What this is representative of is over the 8760 time steps, what is the beam shade fraction loss, over that full 8760? And this is not equated to an irradiance loss because, at this point, we haven't done any sort of transposition modeling. We don't know what the actual irradiance would be for each time step. And a good way to think about this is if, the morning and evening sort of time steps are weighted the same as the midday time steps. So that's a good way to kind of think about that. Okay, so we have our results in terms of the beam shading losses. Let's step out of this. And now this is complete and we're ready to run the prediction. So I'm going to go ahead and run the prediction. And then we'll be able to compare the 2D versus 3D and see how much of a difference that made. And another important point is, the prediction itself should not take any longer to run with a shading scene. So really the computation time associated with the shade modeling is taken up in running the shading scene. Once that's done, the actual prediction itself should not really take any longer than a standard 2D prediction. And of course, as I say that, this particular prediction seems to be taking a while. All right, you're witnessing the joys of a live demo and what can happen. So this is quite odd. Let me refresh. Okay. So I have a feeling this is going to complete pretty quick, but in the meantime, let's step over and inspect the 2D results. And I'll go to draft shared. These are the two that I cared about. So the 2D results, if we look in the results here, the specific yield 1764, and the near shading on global is 6.85%. Now remember, this near shading on global, it includes the beam shade losses as well as the diffuse shade losses. So this is not, just the beam. This is the total near shading loss. So we're at 6.85% here. And then if we step out like here, this is really taking its slow time. There we go. I'll put some more appropriate. It's great because I think I ran this maybe 4 or 5 times before, just to make sure it ran smooth, and it never took more than about 10 seconds. And of course, during a live demo, things are gonna be sluggish. So without stepping into the results, I can say that there was about a 0.8% increase in the overall near shading loss from an energy perspective from the 3D to the 2D. So unfortunately, I think it's time to move on I'll turn it back over to Rafal. Rafal, do you want to take us to the finish line here? And maybe once we get in the Q&A session, I can show that real quick.
Yep, let's do that. All right, so yeah, to close it out before we jump into Q&A, the 3D shading is available now. It's live as a beta for all paid users of PlantPredict. If you're a new user, sign up for a free account at plantpredict.com and click the button on the website to schedule a personalized demo. We could go through one of your actual project locations and discuss the kind of use cases. So it's not a universal demo. We could actually do a demo just for you, to deal with your pain points. And then coming up, our next webinar will be another demo of Terrain Pro. This was a really big hit at RE+. That's our earthwork assessment for terrain following trackers. And we're going to be addressing some of the key feedback we learned. And we're going to be teaching you how to import your own topo and layout data. Next slide, please. So once again, with the 3D shading, we have the Pro and Enterprise suites, which normally include, Design Pro, Terrain Pro, and Voltage Pro. That's the more expensive suite, but 3D shading is available to everybody right now, down to the individual and business level subscriptions. So once again, if you're a paying customer of any kind, you could jump in and go check out 3D shading right now. All right, and with that, we're going to take it into Q&A.
All right. All right, so I think we've got about 5 minutes left, and I just want to reiterate that any questions that we don't get into live here, and we've got quite a few. I think we've got like something on the order of 20 questions that have come in. So if we don't get to them live here, we will respond in writing to all questions separately, probably within the next couple of days to a week. And before we get into questions, I do want to make one correction. So thanks, John from Array Technologies. He has corrected me that their API runs on 5-minute weather interval data, not 15-minute weather data. So I just wanted to make that correction. Thanks, John, and sorry for misspeaking there. So let's hop into the first question. So there's quite a few questions about file formats and is PlantPredict compatible with several questions here, SHD files, DAE, 3DS. So at the moment, the simple answer is no. So SHD is kind of a proprietary format to PVSys. I know that there are applications that can generate SHD files, but at the moment, no, we are not compatible with any of those file formats. That said, the DAE file format is effectively in the format of a PVC file. It's just that the PVC file has a little bit of additional information. So it's a very easy step to go from DAE to PVC programmatically. But we hope to be, extending the capabilities of PlantPredict to bring in other types of file formats from other types of applications as well. It's just that once we do that, we may have to supplement additional information separately. But yeah. Next question is, in your demo, you modeled whole trackers. Can you model individual bays or individual modules? So the answer is yes. And really that comes down to how each object is defined in that PVC file. So the shading scene is really reading the PVC data. And in that PVC file, that's where the sort of boundaries of each polygon, each shading object are defined. So that can be defined at a module level, at a bay level, or at a full tracker level. So hopefully that's clear. So let's see, what's another one? Are there plans to add other trackers into the irradiance optimization dropdown in addition to Array Smart Track? So yes, we're hoping that this is a first step of many, first integration of many, although Array Technologies is set up in a way that I think it makes generally their trackers are gang trackers, and so they follow similar tracker angles. Being able to do this on an individual tracker basis is a little bit more complex. So, but yeah, the plan is to extend that further. Let's see. Let me see if I can find one for Kurt here. There's quite a few questions about file formats and getting information from AutoCAD, etc. What is the working group for integrating electrical and mechanical relationships into the PVC file? And are they taking new participants? Kurt, do you want to maybe speak to your involvement there?
Sure, yeah. The working group is a working group that's run by Sandia National Labs and funded by Terabase. It has all of the major modeling and layout companies involved. If you are interested, shoot me a message or drop your email address in the question area, and I will add you to the group.
Cool. And maybe one last question for you, Kurt. So there's a question, if you were going to be speaking to what the rear shading view factor is compared to other categories.
Yeah. So on the rear side, we just take basically like the system definition. In PVSys, you have like your orientations and your 3D shade scene, and they're completely separate. In PlantPredict, you have your design, your 3D shade scene, and your like blocks and arrays, and they're completely separate. So we take the bifacial gain from the orientations section of the model. And we just use the NREL bifacial view factors model.
Great. Okay. Thanks, Kurt. So I think we're a minute over. I'm going to cut it here. I do want to say that copies of the presentation will be sent to, or links to be able to view this presentation will be sent to, and really a recording of the webinar will be sent to all registrants. And again, we will get to all of your written questions within the next week. So thank you so much for joining. Hope you found it enlightening, and appreciate you guys attending. So thank you.